these are things that you pretty much already know, but let us discuss, just for the sake of clarity, that here you are, and you throw up something, and it goes up to some level. So there is an initial velocity v0, and before it turns around it would stop, so the final velocity would be 0, right? So always remember that if it's going all the way up and about to turn around, the final velocity vf must be 0. So that will not be given to you. That's something you're supposed to figure out. Now, we know that in a problem like this, we are taking for now the upward direction to be positive. Acceleration will gradually is downward, and that's minus 9.8 meters per second squared. Let's say v0 is some number, just for the sake of specificity, 4 meters per second. Okay? So let us calculate the time of flight. So we can calculate the time of flight in two different ways. One would be that, let's label these. We are going from point A to point B. So we have the kinematic formulas that we can use. We have V final equals V0 in general plus acceleration times time. V final square is V0 square plus twice acceleration times distance. Let's call it y because it's vertical. And we know that y equals v0t plus 1/2 at squared into. These are our three main kinematic formulas. And then we have distance traveled, vertical or horizontal, is some average velocity times time. So these are our four equations that we have. By the way, don't jam up the back because I'm going to give you a quiz. And people are sitting right on top of each other. That makes not only our life difficult, but also makes your life difficult as well. So, all right. So anyway, so in this case, since the final velocity is 0 and we are looking for time of flight, it's natural to use this one. You don't have any other choice really. So V final is 0. V0 is plus 4 meters per second. Plus acceleration is going to be minus 9.8 meters per second squared times time. So therefore, it's been quite easy to see that this t is going to be 4 divided by 9.81. I'm going to make it into 4 divided by 10. So you can make it into a 9.8 if you want. It doesn't really bother me if you do that. And then it turns out that your time here will come out to approximately 4.1 seconds. So it's very easy to see that the total time taken for it will go up. And therefore, since we want to know the time of flight basically means all the time it's flying. So it's going from A to B and then back again to A. And so therefore, time of flight will be twice this amount. So that will be approximately 8.2 seconds as I'm approximating now. Okay, any questions? All right, you shouldn't have any questions. All right. Now, the reason why I did this is not to entertain you, but because there is a learning lesson in this problem. The learning lesson is if I have this problem here, going from this point to that point, so this is B and this is A, and the thing is going up at V0, going here and coming all the way back, and there is no air resistance, vacuum, simplified assumption we made. I could have found time of flight another way. The way I would have found time of flight is that I can note it goes from A to B and then back to A. So what is its net displacement? Displacement is the vector from initial point to final point. So if I'm starting at some point, I'm going all the way up and coming back down, then my net displacement is going to be 0, right? So therefore, I easily note that in this case, I can say y equal to 0, I know v0. I certainly know acceleration. So what is time? So I should be able to find that, and therefore, the third equation up there is staring at you, because that's the one that's easy to use. Y is 0 anyway. So I can write 0 equals 4.00 meters per second times time minus 1/2, 9.8 or 8.1, whatever you want to keep it, or 10 squared times time squared. So this should, by the way, give me the total time. Why? Why should we do this? Right?
When you did 4 divided by 8%, why is it 4%?
4 divided by?
4 divided by 10. Why is it 4?
Oh, okay, it's point, sorry, it's 0.4. I'm sorry. Thank you. Yeah, it's 0.4. Yeah. So this is 0. The total time would be 0.8. Thank you. So what would be the way up? Is this something okay? Can I solve? What will that time be? You think? Will that be the total time of flight or half the time? Don't just stare at me. Total time of flight. Why? Because displacement has been put to 0. I put in the final point where it should be and the initial point where it should be, right? So therefore, the total time of flight is what is being calculated here, because this is 0. I'm not giving the distance from here to here. I'm essentially giving displacement from here to here and back here. So therefore, I should get the total time of flight. So I should be able to write t times 4.00 meters per second. And here I should be able to write 4.9 meters per second squared times t squared. So therefore, t is going to be 4.9 divided by 4, and whatever. 4 divided by 4.9. I'm sorry. 4 divided by 4.9. I'm losing my mind. Seconds. And so this would be approximately 0.82 seconds, or 8 seconds. Basically what I'm doing here is I'm cancelling out one of the times because I have time on both sides of the equation. Now tell me one case where I can't cancel out both the terms. Just the way I did. No, just for the same equation. I can't cancel out t quite the way I did. Someone at the back, yes.
If total displacement wasn't 0?
No. Everything is the same as it is. So I'm not going. Yes.
Negative time.
Time won't be negative, so even then it would work. I can't do what I just did. So when would that be the case? What's going on back there? Yes, you. Don't socialize. This is not a social hour. What? Negative what? I can't hear you. But anyway, don't talk. If you have a question, raise your hand and get it answered. You are late, more than 10 minutes late. That automatically qualifies you for a 0 in the quiz. So don't do that. Yes? No, you guys are thinking too complicated. Yes?
It's a B but this is from just A to B, not the displacement. You don't have the numbers.
It's much simpler than yes?
T isn't squared.
No, T is squared. You can't.
I'm saying, like, you can't cancel it.
Yeah, but that's like going around the problem. You already have a t square and a t, right? So what I'm saying is you can't cancel. When can you can't cancel? Yes.
There's no t variable.
Huh?
There's like no t variable atoms.
No other?
Even when there is.
No. Yeah. Yes, the t is 0. My goodness, you guys are really fried by this one. What happened? If t is 0, you cannot cancel because you cannot divide by 0. That's why. So you have to make this determination implicitly as you go down the road because you encounter cases where t equal to 0 is a solution. And just by cancellation, you got to know that you are ruling it out. Okay? So if t equal to 0, if that is a viable solution, in which case it is, right? If t were 0 here and here, the equation would be satisfied very happily. So, but that's not a solution that we are looking for. Basically, what it's telling you is that if this ball never really left my hand, then time would be 0. Somebody is very late. Why are you coming in so late? You're not going to get a quiz today. All right. Don't go at the back. Just come around the front. Don't come in at such a leisurely pace at 9:45. This is not really a coffee hour. All right. So you understand what's going on, I hope. Let me now give you a problem that might come in handy someday. Questions? All right. So what's the problem that's going to come in handy? Suppose you're speeding. Why was that fun? Suppose you're speeding and you are caught. So let's say how that can happen. This problem is not the easiest problem. So let us say you are going at some velocity. You are going at velocity. This is v, let's say vc, signifying your car is going at a velocity of 30.0 meters per second. Okay, that's your velocity. Suppose that's above the speed limit. All right. And suppose that a cop sees you after you have traveled a distance x0. And this x0 is, let's say, 20 meters. Okay? And suppose the cop decides to accelerate at 5 meters per second squared. So the question can be asked as to when will you get caught? Now, a problem like this is not easy. Okay, a problem like this is not easy. So if a cop catches you, or let's say equivalently, you are meeting somebody, right? So what do you discuss before you meet somebody? What are the two things that you need to fix if you're going to meet somebody? Place and time. So if a cop catches you, then you got to know two things, right? You got to know where the cop will catch you and when the cop will catch you. There are two parameters involved in a cop catching you. So let us say the smart thing to do here would be to put this problem in some sort of graphical analysis mode, okay? So let me try to make this as straight as I can. I don't know if it's straight, but it doesn't matter. So let us say that since time is the independent variable which I cannot control, I'll put time along the x-axis, and I will put distance traveled here, displacement along the y-axis. So let's say that you are coming along, and this is you. This is C, let's say, because this is your car. And let's say the cop basically starts 20 meters ahead of you. So the cop starts somewhere around here because this is x, right? So wherever you are coming from, let's make it to x equal to 0. That's by choice. And all I need to then mark is that this x0 is the distance where cop is starting from. And let's stop the clock at the same time. So as the clock starts, that's the point from where we are interested in time. Because until the cop saw you, who cares? Right? You could do anything you want. So let us now say the cop accelerates. How should this curve look like? Or should it be a line? Cop is accelerating. If the cop is accelerating, what should x versus t look like? That's the first thing, yes. Parabola. Because if it's fixed velocity, then there should be a line, just like this. Now that it's not fixed velocity, it should be a parabola. So therefore, I should have a situation like this. So unless you can visualize a problem, rest assured that you will not be able to do it. So therefore, visualizing this problem before you even get going is very important. All right? So let's call this line A. Sorry. A. Any questions so far? Do you realize that yes?
I don't understand why
Why is the curve?
Yeah.
Because the top is accelerating, right? If you're accelerating, then you can see from the third equation there on the right, the distance traveled is 1/2 acceleration times time squared. That's a parabola, right? So time is along the x-axis, y is along the vertical axis here. So if you have an equation which has the form of y equals some constant times x squared, that is the equation for a parabola. Something you should know, right? Any other questions? No? All right. So how do we do this problem? So the question is, how long does it take? So we therefore need to find the time here. Actually, we need 2 times, because we have time t1 and another time here t2. This problem is not, by the way, in the book, so you need to be sure that you, because this kind of a problem actually will come around. That's why I prefer to do this problem, even though it's not actually worked out in the book in that chapter 2. So at any rate, let us set up the equations. The equation for A, so I call it A colon, would be A is, let's say, the place where the cop catches you. In this case, we generically call it x final. Okay? We generically call it x final. So I can say x final minus x0. That would be the displacement of the cop. So x final minus x0, since the cop is starting from rest. So let us make sure that we put that in. So as far as so this is for the cop. So I'll put a C here, just to be clear. And so I can say that, okay, anyway, so that's not a problem. So let's go ahead. The initial velocity of the cop is 0. Oh, I was going to write the initial velocity of the cop. So V0 of the cop is 0. So let us say the first term here would be 0 because you have 0 times t then. And the second term, since the cop is accelerating, would be 1/2. Cop is accelerating at 5 meters per second squared. So 5.00 meters per second squared times time squared. We can even call it t final, just to be, I might make it t final. Questions? You guys okay with it? Yes.
Does gravity have any particles?
No, it is. Thankfully, you are not falling in the zombie trying to fall faster than some of the Superman movies. Okay? So, which by the way is physically incorrect. All the Superman movies that you can see where somebody somehow falls faster and catches you, that doesn't work. Especially if it's free fall. So all that is nonsense. Anyway, all right. That's a good question, by the way. So, all right. So this is my story for A. What about C? Now, C is a very simple story, right? C is distance is velocity times time because there's not much else I can do. So as far as C is concerned, the final distance xf is the velocity, which is in this case 30.0 meters per second times t final. All right? Any objections? Okay. You get it perfectly, crystal clear. That's my assumption. Is that correct or not? That means you didn't understand anything. The response I'm getting. What did you not understand? Yes?
C is the second one out there.
C. No. C is the notation for the car. A is the notation for the, both are C. So I made the cop into an A. What else did you not completely understand? Yes?
I thought the cop was A.
Yeah, the cop is A. C is the car. Now you are really confused. You see, A is the white.
Yeah, that's the cop.
Yeah. So what's the problem? You didn't have breakfast?
I did actually.
Okay. Then you should be able to understand. You have enough.
No, we get it.
Enough nutrients in your body. All right. Any other questions like that? No? You don't want to make a fool out of yourself? Yes. What is that?
T next to 0. Is it TF or TF?
TF. Yeah. T final. That's a handwriting problem. Physics problem is what I'm seeking. Yes.
The VOC is the police car or your car?
VOC is the oh, you're right. That is a legitimate. VOC, it should be VOA. It's a very good question. See, I made a mistake and you caught it. Brilliant. That's what I want. It's VOA because that's the cop. Cop is A. Yes.
So the acceleration is also for supposed to be the cop, right? It's for us.
Acceleration of the cop. Yeah, you are absolutely right. This should be AA. All right, good. Now we are making progress. See, you are saving me from getting confused down the road. Who else has another observation or problem? So I did everything right. If I make a mistake, it's your problem. If I screw up at this point, you are, yes.
You forgot to ask the distance for that's an international
20 meters per second is how much the cop is ahead of the car when the cop is taking off. I have actually subtracted it from the distance the cop traveled. So x final is the distance that the car travels before the cop catches it. So the distance the cop travels must be this x final minus x zero. Okay, so that's not a problem. Do not talk. You're playing with fire. Okay. All right. Since you guys have no objection, I will try to proceed. So what do I have to solve for? I have to solve for T final. Let me write T final here. And solving for T final means solving these two equations as two equations. Here, I don't know x final, I don't know t final. So I can actually calculate both of them, x final and t final, because I have two unknowns and two equations. That's pretty good actually. So what I could do, what would be the smarter thing to do here, would be I can probably, there are quite a few ways of proceeding at this point. So let us say I want to try to take the first equation. X final minus x zero is 1/2 5.0 meters per second squared times E final squared. Right. Please don't talk. I'm hearing some voices, whispers, but they're not particularly pleasant to hear, so just stop. So I can then write this x final as 30 meters per second times t final minus x0, which I know x0 is 20. You're still talking, I can hear you. T final squared. Did I do it correctly or no? Did I do it correctly? What's the guy next to you? Yeah. But why is his head down? Very good. Take to your phone, right? You're saving to your phone, right? No, not you. This guy here. What are you doing? Reading a book? No, the one behind you. What are you reading a book? Or reading it from your phone? I catch you with your phone. My dear, you're half an hour late. You're not going to get a quiz today. You're not going to get a quiz today. You're half an hour late, yes. T final comes from the left side because I'm just putting in. So x final here is T final, this thing. Okay? Any questions? Yes.
Where'd you get minus 20 meters from?
Minus 20 meters was x0, right? Except minus x0. So minus.
Oh, okay.
All right. Yes. X0 is how far the cop was ahead. How far the cop was ahead when he saw the car. So 4 people today came late. None of you get quizzes, okay? Because there's 0 in the quiz. So just mark it up. Rufeng and Rance wouldn't know, but Rufeng, please know that. Any other questions? All right. So we should now be able to solve this problem because what we have is a straightforward quadratic equation. So we can write 2.50. Let's say I now directly write a quadratic equation. I'll take this to the other side, plus 20.0 minus 30.0 times T final plus 20.0 equal to 0. So I'm dropping the units because now I'm interested in solving the quadratic equation. So this quadratic equation can so I can basically think of it as ax squared plus bx plus c equal to 0. So then I can write x equals minus b plus minus b squared minus 4ac square root over 2a. So I should now be able to write minus b, so minus b would be plus 30. Plus minus 30 squared should be 900. Minus 4ac, so minus 4 is the number I'm carrying. A is 2.5 and C is 20. Right? Yeah. So now I will put this on a roof and then twice A. A is 2.5, so this would be 5. Did I do it right? All right, so let me now not show you every step because then I'll never get where I want to go. So at any rate, if you do the calculation now, then T final comes out to 30.0 plus minus 700 square root divided by 5. Square root of 700 is not the most pleasant thing, so it's 10 times root 7. If you play around a little bit with trial and error, the closest you can get to is 2.6. So root 7 is slightly shy of 2.6. 2.6 is 7 point something. So 7.29. So anyway, so let's say if I'm doing it without a calculator, I should be able to write 30.0 plus minus roughly 26 and divide that by 5. Let me now stop worrying about significant figures and everything. So anyway, so this is going to be one answer would be this is 56 divided by 5, so that would be 11.2 seconds is one answer. And the other answer would be 30 minus 26, so that's 4/4 is 0.8. So there are two times we get. The first time, 0.8 seconds, is right around here. So the clock actually catches you first here, and then the clock catches you here. This time is that 0.8 seconds. This time comes out to be 11.2 seconds. So let me just recap this problem very quickly. The first thing we noted is that if the cop is going to catch you, there are two things we need to find. One is when and where. So x final and t final. Then we wrote down the equations of motion for the cop and for the car here. And the car is in pink or orange or whatever the color is, and A is white. Okay. So we eliminated xf from the equation because there are two equations, two unknowns. So we are left finally with only one variable, that's t final. And from t final, we are able to solve the quadratic equation for t final and get to where we want to go. I can also find out easily what x final is because x final, if you look at the simplest of the equations there, is 30 meters per second times t final. So one of these numbers would be 0.8 seconds, and the other one would be 11.2 seconds. 11. So if you multiply out, those are the two values of xf, but the cop will be meeting you. Okay? Any questions? Yeah.
How do you know which one is T final?
How do I know which one? 11.2?
Yeah.
Because I'm solving a quadratic equation, right? So
You get 2 answers.
I get two answers, and both answers in this case are reasonable.
Okay.
We don't have to throw away anything because if you look at the plot, you see that the parabola cuts the line in 2 points. So that's why you're getting the two answers. Yeah.
So 11.2 and 0.8, that's T final and T1.
No, you can call it T1 and T final, yes, if you want, yeah. The answer just spits out both as T finals, both points where they're meeting, yeah. No questions? Yes?
So this cop meet the car twice.
Say that again?
Does the car, the cop catch up with the car twice?
Yes. Somebody just came in. Can you please show your face? Why don't you come here? Because I need to have a chat with you. And you will certainly not get a quiz today. You realize that because more than 10 minutes late, you don't get a quiz. So please come and sit here. We have to have a serious conversation. You can't do this in my class. You either then drop the class or get serious.
To go back, so I think there may be some confusion on how the cop is catching the car twice. Exactly what physically is.
Good point. So Rance would like me to explain to you why the cop is catching the car twice. Well, in this case, I did not get into that because I don't particularly have any interest in what exactly the cop wants to do. But the thing is that as the cop speeds up, the first time the cop sees the car and can catch the car is at A. So you can argue that that the cop will catch the car at 0.8 seconds and get done with it. But the complete solution to the problem demands that you realize that the cop actually catches the car twice, and the second time would be at 11.2 seconds. So basically, that's how this problem ends up. So if I ask you, for example, what is the earliest time in which the clock catches the car, then your answer should be 0.8 seconds. But if I don't tell you anything, then both answers is what would be the right way to report your solution. Okay? Questions? All right, yes?
In the problem, did you have to report X final? Is that why you substituted the time?
In the problem what?
That you like substituted T final into X final? Did you have to calculate X final?
If you are asked to do, because there were two unknowns. X final was unknown, T final was unknown. There were two unknowns. So for two unknowns, it's a quadratic equation, so you can find both of them. All right, let's move on. Because I have quite an agenda today. By the way, any of you had trouble with the problem in which this thing was dropped and there was a sound thing coming back up? All right. So I'm not going to, yes, you had a problem with it? You had a problem with it? All right. Let me just quickly go over it because I don't want to work it out on the board. The solutions are already there. So if you drop something, this thing goes and hits the ground, but your ear is here. So the sound now has to travel from the bottom all the way up to your ear. Okay? There are two times then. One time is the fall time of the object, and one time is for sound to travel all the way up to your ear. So let's say T1 and T2. So the first thing you notice is that the two times add up to 2 seconds in the problem that I gave you. So T1 plus T2 is 2 seconds. That's one condition. Finding T1 is quite easy because it's just a ball drop problem. You have done that a million times already by now. So that you know, it's half gt squared, essentially false. So that's half gt1 squared. That would be, so the y is half gt1 squared. And as far as the sound is concerned, the sound speed is given, 332 meters per second in the problem. So you multiply the sound speed with T2, because that's how long sound takes to come back up. So you have, therefore, an equation for T1, which was the y equals 1/2 gt1 squared. You have sound speed times time, also giving you the height. And you have T1 plus T2 equals 2. So you have three unknowns, T1, T2, and y. And you can find all of them. Okay? Fair enough? Not fair enough. All right. Well, you have the solutions. You better study it. I assume you know. You know what we have done. All right. So now we'll switch gears a little bit. I'll get into vectors. And before I get into vector algebra, so let's just quickly note a little bit about vectors. So examples of vectors would be, for example, displacement. As I said, displacement is final point minus initial point, and the direction in which you're going. So both the things are involved. So displacement, therefore. So if I go from point A from B, and I go like this, then displacement really is this vector. Okay, so it's pretty simple. Displacement is you go from initial to final. Shh. What's going on? Don't help him. Yeah. Do not help him. He can seek help from me. He's an adult. So, all right. So that's that. And then the next simple vector that we have been talking about a lot is velocity. All right? So velocity is same as speed, excepting there is a direction. So I can say, I'm going from north to south around transit road at a speed of, let's say, I usually like to speed a little bit to maybe 60 miles per hour, and therefore you can immediately infer that my velocity is 60 miles per hour because I not only told you that how fast I was driving, I also told you that I was going from north to south. So there is a direction information. Likewise, there is acceleration. So acceleration basically is how I'm speeding up. For instance, I'm starting my car from rest, so it's 0 miles per hour. And by the time I get up to the top of the parking lot, it's 20 miles per hour. So I've gone from 0 to 20, and let's say I went from 0 to 20 in 1 minute, 60 seconds. So therefore, the difference between final velocity and initial velocity would be 20 miles per hour, divided by 60 seconds, I have to do unit conversion in this case, and I can find the acceleration. I've already given you the sense of direction from here to there. So these are all examples of vectors. We'll be dealing with vectors a great deal. So therefore, that shouldn't be a problem. Now let me ask you a quick question. Suppose I make something go around the circle. Let's have a piece of rock on this plane, and it's going like this, and it's going at some speed, let's say, of 5 meters per second. So the speed is 5 meters per second. What is its velocity? Does it have a velocity?
No.
Because it's going in a circular track. So if I have to describe its velocity, what should I do? Make a point. Just a point? So suppose I want to know the velocity here. I have to basically say whatever the speed is, 5 meters per second, and the momentary instantaneous direction, which would be like this, which should be a tangent to the circle. So 5 meters per second in that direction, right? So likewise then, the reason why we can't really discuss velocity so simply is because at this point, this is the tangent, this is it. At this point, this is the tangent, so this is it, and so on. So you see here the velocity is continuously changing. In fact, what you can already see is that the velocity actually is changing in such a way that it's being pulled inward, right? It's being pulled inward. Because if you weren't pulling it inward, the thing would go straight. It's like after a little bit of time, you pull it inward again. Velocity is that way. After a little bit of time, you pull it inward again. Velocity is that way. So it's now going around in a circle. So in other words, in this case, the velocity actually can argue is changing. And if the velocity is changing, that means there's acceleration. And we'll discuss later that the direction of this acceleration is inward because you're continuously being pulled inward. Okay? I wanted you to kind of appreciate that because we'll come back to this point in a very, very big way very soon. So you can have very simple linear acceleration. For example, you're driving a car, you're speeding up, and you can also have a scenario where you're being continuously pulled inward. So therefore, the acceleration here is towards the center. And this is called centripetal acceleration. There are plenty of examples of this. When you're driving a car and take a turn, for example, you will feel the effects of centripetal acceleration. All right, so let us now that we understand that vectors have both magnitude and direction, the most important thing that we've got to learn is how to add and subtract vectors and so on. And then later on, we'll deal with multiplication of vectors. We won't do that now. So normally, we denote a vector like this. What do I mean by like this? That means this thing has a length, and this length denotes the magnitude of the vector. Let's say I'm talking about a velocity v of 5 meters per second. Then according to some scale, according to some graphical base, I'm going to make this length such that it reflects 5 times my unit meter per second by choice. And the direction should tell me in which direction the velocity is. So if I'm going northward at 5 meters per second, let's say this is north, then it would be like this. If this is west, it will be like this, and so on. Okay? Sorry, what am I doing? This is east. It will be like this and so on. All right. So now we want to find out how to add vectors. How to add? So how do you add? Well, let's say I have two vectors A and B, and let's keep things simple as we are trying to understand it. Let's say A is this way and B is that way. And suppose I want to add the two vectors, so I want to add these two ones. Okay? Any questions so far? Yeah.
Will south and west usually be negative?
What?
South and west vectors will usually be negative because it's a downward
convention.
It can be, yeah. I mean, that's a more common choice. It doesn't have to be. It's a matter of convenience at the end of the day, as long as you're consistent. So, all right. So in this case, I can do this addition graphically. So let me just show you the graphical way. The graphical way would be, I can take this vector like this. I can redraw it, keep everything the same, the length the same, the direction the same, and take this vector and literally, quote unquote, translate the vector. What does translating a vector mean? That means I take it here and let's say put it here. So this is the tail of a vector. This is the tip of a vector. So this is the tail and tip of A. And as far as B is concerned, this is the tail of B and this is the tip of B. So what we have really done is put the tail of one and the tip of the other, kept the direction the same and just moved them around. So in this case, it will turn out that if I draw this line, this would be the actual resultant summed vector. So if I call the resultant vector C, then this will be C. So that's one way of doing it. The other way of doing the exact same thing would be, I can put A here, and then instead of putting the tail of B at the tip of A, I put both the tails together. And that would also have the exact same effect, except now I'll complete the parallelogram and draw the diagonal. And this diagonal now will turn out to be the resultant, it's called a resultant vector, the sum of the two vectors, resultant vector C. So, generally speaking, the graphical addition is an excellent visual tool. So when you're solving a problem, if you do this graphical addition, then it turns out to be a very, very good way of visualizing where your resultant vector should be. But this is not the most convenient way, because you may be asked to sum many vectors, and all these vectors may not be pointing in such nice directions. So what do you do in that case? Well, what we need to do is we need to master how to solve vectors algebraically. How to add vectors algebraically. So the way you add them algebraically is actually quite simple. Suppose I take two vectors P and Q, and I want to add P plus Q, and let's say P is in that direction, and Q is in some other direction like this. Now, well, that's too much. Maybe like that. That is Q. Now that's not a very good looking situation. So the natural thing to do now would be to do it algebraically. How do we do it algebraically? I basically draw axes. So this is my x-axis, this is my y-axis, this is my origin. And I put the P here, I translate it, as I said, to this one. So in other words, I take this vector literally and bring it here. So in other words, I draw a line parallel to this, make it the same length, give it the same direction. And likewise, I can also make a Q here. So this is P, this is Q. And let's say for consistency's sake, I give them the angles theta. So this angle here that P makes, let's say, is theta 1. And this angle here that Q makes is theta 2. So what I'm trying to tell you is that these angles are being measured from the positive x-axis. You need to be very careful about how the angles are measured. So for example, I don't have to measure angles always from the positive x-axis. But that is the simplest and the most conventional thing to do, because that simplifies some things down the road, or it could simplify some things down the road. So now what I do, let's say I blow up exactly what's going on with P now for a change, and say this is theta 1. So I want to resolve. The word is resolve P. To resolve P, I stand here and draw a perpendicular. So this is a 90 degree, and this piece, because it is sitting on the x-axis, is P sub x. And then likewise, if I drop a perpendicular on the y-axis, this piece here would be P sub y. All right? Any questions? So P sub x, now let's look at this right triangle. If this is a right triangle here, then this is P sub x. If the vertical piece is P sub y, that means this also must be P sub y. This is theta 1. So if I say sine of theta 1 would be opposite over hypotenuse. Hypotenuse here is actually P itself, the magnitude of P. So opposite would be Py over the magnitude of P. So therefore, if I know the angle, I can actually find Py, because Py is going to be the magnitude of the vector P times sine, in this case, of theta 1. So similarly, I can find P sub x as well. So P sub x, if I look at the same triangle, would be given by P cosine of theta 1. Because you see, if I look here, then cosine of theta 1 is going to be P sub x, because that's the adjacent over P. No, there is no magnitude here. This is what it is. So P sub x is Px cos theta 1, and P sub y is P sine theta 1. So if I'm adding P plus Q equal to, let's say, R, I give it some name, then it is important to notice that I can write a P sub x, which is P, in this case, sine theta 1, sorry, P cos theta 1, P sub y as P sine theta 1, and in the very same vein, I can write Q sub x as Q cos theta 2, and Q sub y, I can repeat what I did basically without any further work, sine theta 2. Any objections so far? Anything that you don't understand? I'm just dealing with the right triangle. So if you are not up on your trick, remember I already told you. If you guys need any special help in math, I'll consider giving a special class on a Saturday. But I only got 2 responses. That's why I haven't made any noises about it. It's not worth doing something for 2 students if they're, yeah.
So will we be able to estimate angles to make them simpler, or?
Yeah. I usually give simple enough angles that you don't have to use the calculator unless you're doing a book problem. Okay? So, alright. So now you see both of these Px and Qx are sitting along the x-axis, right? So if I actually draw this thing, then this was my Px coming out of here, and this was Qx. Sorry, this was Q, this was P. So Qx would be here. This piece here is Qx. So as far as summing the 2 vectors goes, I can say that the x component of the resultant R must be the sum of these 2 guys along the x-axis. What else can it be? Okay? So therefore I can write that Rx is P cosine of theta 1 plus Q cosine of theta 2. Similarly, Ry would be Py plus Q sub y, so that would be P sine of theta 1 plus Q sine of theta 2. So this is just the magnitude of P and magnitude of Q is what I'm writing. Okay? Any questions so far? Okay, so this stuff is not very difficult. What becomes difficult though, where people make mistakes, is in how to add them in practice. Because right now we can actually find the qx and qy's quite easily, right? As long as you can resolve px and py, qx and qy, at this point for q, you have a calculator, you can find sine theta 1, cos theta 1, and so on. Make sure that your angle is properly done. So if your angle is in degrees, and you're using a calculator, your calculator should be set for degrees. Your angle is in radians, if you're using a calculator, it should be done in radians. If you get a bizarre result, that's not because the calculator created some black magic, it's because you screwed up. So make sure that you are at home, that is, they can deal with the calculator's results. All right, so now you see, I have a resultant vector. And this resultant vector Q is what I have to find, and I do know what Q sub x is from there and Q sub y is from there. So one question is what is this angle, the other question is what is its length. So length is very simple. So as far as the length of Q is concerned, which I'll call Q now, this is going to be Qx squared plus Qy squared by Pythagoras theorem square rooted. I can call it mod, and it's a positive number. And as far as the angle is concerned, let's call this angle theta. It turns out that since you have the opposite and the adjacent, the appropriate quantity here would be tan of theta, which is opposite over adjacent. Tan of theta is Qy over Qx. So therefore, if you want to look for theta itself, you have to do an inverse tangent or arctangent of Qy over Qx. So this then gives you the recipe for not only adding two vectors, but for as many vectors as you wish, because all you are doing is taking each of them, you are resolving them along x and y, you are noting down all the ones that you need to add or subtract, as the case may be, and then you simply do the addition to get qx and qy, and then find out the magnitude of q and the angle of q. So there are multiple steps in this problem, and I've just taken you through all these steps. Now, there's a little bit more here that I would ideally like to do, but I don't really have the time. Some simple angles you need to know. For example, let's say, how do I write it? I can write theta, sine theta, cos theta. Tan theta is of course sine theta over cos theta. So this is not important. If you know one, you know the other. So theta is 0. Turns out that sine is 0. Cos is 1. Theta is 30. Sine 30 is half. Cos 30 is root 3 by 2. 45. Both are root 2 by 2. This you got to know. All these. 60 is root 3 over 2. But I'll show you a very easy way. This is half. And 90, sine is 0. Sine is 1. And cos is 0. What is the easy way? Since 1 and root 1 are the same, you can just remember this series, this table. So basically, as theta increases, sine increases. Half, root 2 over 2, root 3 over 2 to 1. And this goes down just the opposite way. So this is 1, that's 1 and 0. And everything is just flipped. And then you can calculate tan theta in the same. So at this point, you should have no difficulty doing all the angles between 0 and 90. Next week, right now, since you'll be using calculators at home for doing the problems I assigned, I don't have to worry about it, at least not in a big way. But as I start my class next week on Tuesday, I'm going to show you how to actually go and calculate the values when you have angles greater than 90 or greater than 180 in particular, just without having to do any calculators and using the trig identities. You just need to know a few trig identities. Most of these, though, if you get really stuck in, I help you. So that's not a huge problem. All right, let's go to the quiz now. Those of you, 4 of you who came late,